Hello class, today we're learning about continuity. So I had you guys do some other activities about continuity, but we know from advanced functions that a continuous function is one where we never have to lift our pencil when we're drawing it. There's no breaks or anything like that, but we can use our knowledge of limits to further define what continuity means at a point, and we can get much more rigorous with it. Okay, so we're going to learn today whether a function is continuous or not using limits. So a continuous function has no gaps. A person can draw a continuous graph without lifting their pencil from the page. To say a function is continuous at a point is to mean that the graph passes through the point without a break. Functions that are not continuous may still be continuous at certain points. So I've drawn here one function that is continuous over its entire domain. You can draw one similar. And then in this graph, g at x is actually discontinuous at x equals 2. So overall, we would say it is a discontinuous function, even though it is continuous everywhere where x does not equal 2. So something to note is that all polynomial functions are continuous over their entire domain. But a rational function, f at x over g at x, is continuous at x equals a, provided that g at a does not equal 0. So in other words, I'm just making this bigger. In other words, a rational function is continuous except at the vertical asymptotes. Okay, so now we have three conditions for continuity. So for f at x to be continuous at a, first of all, f at a has to be defined. Okay, we actually have to have something existing at that point. The limit as x approaches a of f at x exists, so the limit exists, and that limit equals that defined point. Okay, so that has to have a defined point, the limit has to exist, and they have to be equal to the same thing. So in other words, as x approaches a, the points on both sides converge to the point where it actually exists, ensuring that f is unbroken at that point. So when I ask you, or a question asks you about continuity, the burden of proof requires all three things to be met. So on your test, when you're asked, is something continuous, you need to think of these three things and show that all three are true. It is not merely enough to show or just say yes or no. You have to meet all three conditions for continuity. So this does not necessarily go both ways, though. If a function is discontinuous at a point, it does not necessarily mean that there's not a limit. So that's interesting. And where is my pen? Here we go. So this is interesting here. I'm just going to get a bit of a thicker weight. So, for example, a whole. So just because it's not continuous doesn't mean we don't have a limit. So for example, we could have a function like this that has a hole here and moves on. Doesn't really matter. And also exists here. So in this case, we'll say this is f at x. Okay, so this here is L, so that's the limit, and this here is f at a, if this is x value is equivalent to a. So in this case, we can say f at a exists, and the limit as x approaches a of f at x is equal to L, but f at a does not equal L, so therefore it's discontinuous there. At x equals a. Okay, so an infinitesimal whole is the only place where a function can have a limit where it is not continuous. The limit of a whole is the height of the whole. Okay. So now let's move on to this example where I want us to actually graph this piecewise function. So to graph a piecewise function, we're going to check what's going on the fence here. So this first function owns the fence, okay, of 1. The value of 1 actually goes into the 2x squared plus 3. So f at 1 is equal to 2 times 1 squared plus 3. So it's equal to 5. Okay, so let's go. We'll say 1, 2, 3, 4, 5, 6. We'll say 1, 2, 3. So 1 is 1, 2, 3, 4, 5. Okay, so we're seeing if it's continuous at that. So for graphing purposes, let's just throw in some other things. So let's throw in f at 2. So that would be 2 plus 4, which is 6. So we get this here. If you put f at 3, you get 3 plus 4, which is 7. So you're just getting this linear relation here. What do we get at 0? 0 is 3. And -1 is 5. So you're getting this parabola on this side. Okay. So we can see it's continuous, but let's keep doing our burden of proof. So f at 1, that's the first burden of proof. F at 1 is 5. So now let's test the limit. So the limit as x approaches 1 from the left of f at x, well, that would be the limit as x approaches 1 from the left would be filling in that we would then choose the function 2x squared plus 3, okay, because that's what's happening before we get to 1. So that gives us 5. And then we test the limit on the other side. So as it approaches 1 from the right, that's the same thing as saying the limit as x approaches 1 of x plus 4. So that also equals 5. Okay, so the limit exists. So we can say, therefore, the limit exists. The limit as x approaches 1 of f at x exists. Okay, so that's the second burden of proof. And then the third burden of proof is that f at 1 actually equals the limit as x approaches 1 of f at x. Therefore, yes, it is continuous. Sorry if this is behind my head. Continuous at x equals 1 is what we can say. There it is. All right, so that one includes a visual. Now we're just going to do a bunch that don't include the visual. So remember, we're going through the 3-part burden of proof each time. So for this first one, we already know that it's a polynomial, so we can say that it is continuous. So it's a polynomial. Okay, so we can say that f at 2 is equal, if you put that through, you get 13. And the limit as x approaches 2 of f at x is also 13. So therefore, yes, it's continuous. Okay, but this next one you'll notice is rational. Okay, so we can start with g at 2 is not defined. So we don't even need to go through and do the limit because it doesn't matter. Since we've already not met the first burden of proof, therefore we can say it's discontinuous. Continuous. Okay, there we go. So this next one, though, notice that even though 2, if put into this first part of the function, is not defined, but it gives a separate point. So it's saying this is the function, except for at 2, it's equal to 3. So we know that, here, I'll just do a different color so you don't get confused. So h at 2 is 3. So now we have to check the limit. Okay, so the limit as x approaches 2 of h at x is equal to the limit as x approaches 2. Okay, so to solve this limit, we want to factor the numerator. So you get x minus 2, x plus 1, all over x minus 2. So you get the limit as x approaches 2 of x plus 1, which is equal to 3. So the function exists at 2, the limit exists at 2, and notice that these two are the same. So h at 2 is equal to the limit as x approaches 2 of h at x. So therefore it is continuous at x equals 2. Yay! One more question. All right, so here we have a piecewise function. So first of all, our first burden is does the function exist at 2? So f at 2, you go to this part here, since the inclusion is on the second part. So f at 2 is equal to 3, so that's step 1. We're good. So now we need to check if the limit exists. So because this is a piecewise function, we need to do the two-sided limits. So the limit as x approaches 2 from the left of capital F at x is equal to 4 minus 2 squared, which is equal to 0. And we can say the limit as x approaches 2 from the left of f at x, we can clearly see is equal to 3. So therefore, the limit does not exist since it is approaching 2 separate values, and therefore the function is discontinuous at x equals 2. All right, so basically after this note, you should be able to define the 3 conditions for continuity using the mathematical notation, and then use that 3-condition test for continuity of a function at a given point. So thanks for watching, guys. I hope you learned lots.